Every so often, science delivers a reminder that the universe is far better at keeping secrets than we are at finding them. For more than 40 years, astronomers aimed the world's most powerful telescopes at a nearby star called Beta Pictoris, a young and restless sun about 63 light-years away, studying its glowing ring of debris, mapping its dust, and even photographing two giant planets circling it. And all that time, a third giant planet was sitting right there in the same system, waiting to be noticed. The James Webb Space Telescope finally revealed it, but not in the way anyone expected. There was no dramatic image of a new world emerging from the dark, no sudden flash of reflected starlight announcing its presence. Instead, the planet announced itself in the quietest way possible, through a pattern of absorbed light, a kind of barcode written in the atmosphere of the world itself. It is one of those rare moments in astronomy when an object that should have been obvious was hiding in plain sight all along. The story begins with a star that astronomers have loved for decades. Beta Pictoris is young, only about 23 million years old, which in cosmic terms makes it a teenager, still surrounded by the leftovers of its own birth. Around it orbits a vast and tilted disk of dust and debris, the shattered remains of asteroids and comets colliding in the chaos of a young planetary system that is still finding its shape. That disk is one of the brightest ever observed, and it was one of the first such structures ever seen around another star. It was discovered in the early 1980s when the infrared telescope IRAS noticed something odd, a faint glow hanging around the star that did not belong to a normal sun. Follow-up observations revealed the truth. Beta Pictoris was surrounded by a swirling ring of rocky rubble and ice, a construction site where planets were being built. Astronomers understood immediately that this disk was a natural laboratory, offering a front-row seat to watch a solar system form in real time. And because the disk is seen nearly edge-on from Earth, it gives us a remarkably clear view of the very processes that once shaped our own solar system. For decades, every telescope that could see it pointed at it, and every study seemed to add another layer to the mystery of how worlds are born. What made the system even more fascinating was the discovery of planets within it. In 2008, astronomers announced the first direct image of a giant planet orbiting Beta Pictoris, a genuine breakthrough, because taking an actual picture of a planet around another star was still in its infancy. That planet, Beta Pictoris b, became one of the most studied worlds outside our solar system, a colossal gas giant weighing many times the mass of Jupiter and glowing in the light of its young parent star. A second planet, Beta Pictoris c, was identified later, circling closer to the star, and for years the system appeared complete. Two giants, one bright debris disk, and a clean story about how planets carved their way through the dust around a young star. But something did not quite add up. The inner edge of the disk was too sharp. Its structure seemed strange, and a warp in its shape hinted at a gravitational hand that no one could see. Some astronomers quietly suspected that another planet was lurking in the system, a world massive enough to sculpt the debris, yet too faint to appear in any image. They were right, and it took the James Webb Space Telescope, the most powerful observatory ever launched, to prove it. To understand how the planet stayed hidden for so long, it helps to understand how difficult it is to see a planet at all. Stars are blindingly bright, while the planets around them are unimaginably faint, reflecting only a tiny fraction of their parent star's light. A giant planet like Jupiter, seen from a neighboring system, would appear roughly 1 billion times fainter than the star it orbits. Trying to photograph such a world is like standing in a desert at noon and attempting to spot a single candle flame flickering in the shadow of a lighthouse. Nearly impossible without extraordinary tools. Telescopes attack the problem with devices called coronagraphs, which block the light of the star itself so that the faint glow of nearby planets can be captured, and Webb carries coronagraphs that have worked beautifully in other systems. But Beta Pictoris threw an extra obstacle into the path, because its debris disk behaves like a cosmic fog. The dust scatters light in every direction, washing out the region around the star and drowning faint objects in a haze of reflected sunlight. A planet sitting inside that fog becomes nearly invisible, its light blended into the general glow of the disk, and that is exactly what happened to Beta Pictoris d. It was not too dark to be seen. It was hidden by the very material that should have revealed its birthplace. The discovery came about by accident, which is how so many of the greatest discoveries in astronomy happen. A team of researchers led by the astronomer Jean-Baptiste Ruffiot was studying something else entirely, the atmosphere of the known giant planet Beta Pictoris b. They pointed the telescope's NIR-spec instrument at the system and let it stare, collecting the light streaming in from the region around the star for hours on end. NIR-spec is a spectrograph, which means it does not simply take pictures, it splits light into its component wavelengths. The way a prism turns sunlight into a rainbow, every molecule in an atmosphere leaves its own mark in that rainbow, absorbing specific wavelengths and creating dark lines in the spectrum. These lines are so distinctive that astronomers often compare them to barcodes, and reading them tells you exactly which chemicals are present in a distant world. The team expected to see a smooth, featureless spectrum, the signature of light bouncing off dust in the disk. But instead, they saw something entirely different, a clear pattern of dark absorption lines revealing the presence of carbon monoxide, a gas that is common in the atmospheres of giant planets. It was the kind of signal that should not have been there, and it demanded an explanation. At first, the researchers were cautious, and their caution is a lesson in how modern astronomy actually works. The NIR spec data also contained an image, and within that image there was a bright spot of light where nothing should have been, a spot that anyone less experienced might have announced as a discovery on the spot. But the team had been taught by years of hard lessons, because bright blobs in telescope images are notoriously unreliable. They frequently turn out to be instrumental artifacts, glitches in the detector, or features of the debris disk itself. The history of astronomy is littered with objects that prove to be nothing more than noise or dust. The team knew that a bright dot on a screen proves nothing by itself. So they did what the best astronomers do. They looked at the spectrum, the true fingerprint of whatever was shining there, and the spectrum was unmistakable. The carbon monoxide lines also contained information about motion, because light from a moving object is shifted in wavelength, stretched or compressed by its velocity. When the team measured that shift, they found that the object was moving exactly the way a planet would move, pacing back and forth in its orbit around Beta Pictoris. Its position, its speed, and its alignment with the disk all pointed toward the same conclusion. This was not a stray star or a background object. It was a planet, and it belonged to the system all along. The discovery is described in a study published in the astrophysical journal Letters, led by Aidan Gibbs of the University of California, San Diego, who was working alongside Ruffio when the signal appeared. Gibbs later summed up the moment with remarkable humility, explaining that they were not searching for a new planet at all. They were trying to understand a planet they already knew existed, when this telltale signal simply appeared in the data where they did not expect it. That honest admission captures something essential about the scientific process, because the most important discoveries are often the ones nobody was looking for, and the people who make them are the ones prepared to recognize the unexpected when it arrives. In this case, the preparation took the form of Webb itself, a joint project of NASA, the European Space Agency, and the Canadian Space Agency, whose enormous golden mirror and sensitive instruments allowed the team to capture a spectrum sharp enough to expose a planet hiding inside the glow of a debris disk that had defeated every other instrument ever aimed at it. Sometimes the greatest tool is not the one built for the job, but the one flexible enough to stumble onto something better. Once the team realized what they had found, the next step was to confirm it and learn more. So they requested follow-up observations with another of Webb's instruments, the mid-infrared instrument known as MIRI, using a fast-tracked observing program reserved for urgent and important discoveries. Those observations revealed something wonderful. The atmosphere of the planet contained water vapor and methane, two molecules that are characteristic of giant planets, and that told the researchers a great deal more about the world they had just found. The water vapor and methane, combined with the earlier carbon monoxide signal, painted a picture of a genuinely giant world, cold and massive, wrapped in an atmosphere of hydrogen and helium with a rich chemical menu floating above its clouds. The evidence was so strong that the planet was confirmed from the very first observation, without the long process of repeated imaging that usually follows a direct detection. This, the researchers noted, is one of the great powers of spectroscopy, because a spectrum contains an incredible amount of information. You do not simply learn that something is a planet. You immediately begin learning about its temperature, its chemistry, and its motion, all from the same observation. And that efficiency is changing the game of exoplanet science. So, what kind of world is Beta Pictoris d? The measurements suggest that it is at least twice the mass of Jupiter, making it the smallest of the three known giants in the system, although smallest is a relative term when the comparison involves worlds more massive than anything in our solar system. It orbits its star at a distance of roughly 30 astronomical units, where one astronomical unit is the distance between Earth and the Sun, which places the planet in a region comparable to the orbit of Neptune, far from the star's warmth and deep in the cold outer reaches of the system. Its orbit is the widest of the three known planets, and yet it still lies inside the inner edge of the debris disk, right in the zone where the fog of dust is thickest. And that is precisely why it escaped detection for so long. It was not far away, it was not exceptionally faint, it was not awkwardly placed. It was simply obscured by the glowing rubble of its own neighborhood, invisible to conventional imaging, because conventional imaging could not see through the haze. The planet was hiding in plain sight, and only an instrument that could read the light molecule by molecule was able to find it. The confirmation did not rest on Webb alone, which is exactly how it should be in a healthy science. While Gibbs and his colleagues were analyzing their spectra, another team was independently working toward the same conclusion. Ben Sutcliffe of the University of Edinburgh and Marcus Bonza of the European Southern Observatory led a separate study using the Very Large Telescope in Chile, one of the most powerful ground-based observatories on Earth, alongside Webb's own NIRCam instrument. Their data combined high-resolution imaging from the ground with Webb's infrared vision, and they reached the same answer. There's a third planet in the Beta Pictoris system, and it is exactly where the spectroscopic signal said it would be. Independent confirmation of this kind is the gold standard of astronomy, the difference between a tentative claim and an established fact. The two teams found each other's work so complementary that they now describe the picture together, a three-planet system painted by two separate brushes but forming a single portrait. With this discovery, Beta Pictoris becomes only the second planetary system ever found to contain at least three directly imaged planets, joining a very exclusive club that astronomers can count on one hand. There is something almost poetic about the fact that the planet was found because astronomers were looking at its sibling. Beta Pictoris b, the giant that announced itself in 2008, turned out to be the key that unlocked the secret of Beta Pictoris d. The team was studying the larger planet's atmosphere, and in doing so, they swept up light from a wider region of the disk, catching the fainter world in the same net. It is a reminder that, in astronomy, as in so much of life, the search for one thing frequently uncovers something else entirely. But the bigger lesson is about technique. This is the first directly imaged planet ever discovered primarily through moderate resolution spectroscopy, and that represents a genuine shift in how astronomers might find planets in the future. The old method of direct imaging requires a planet to be bright enough and far enough from its star to be seen as a distinct point of light. The new method requires only that the planet have an atmosphere, since every atmosphere writes its chemical signature into the light that passes through it. A planet can be invisible in an image and still announce itself clearly in a spectrum, the way a voice can identify a person hidden in a crowd. The implications reach far beyond one star system 63 light-years away. Consider what happened here. A giant planet hiding in plain sight was found inside one of the brightest debris disks known, an environment that had defeated every imaging technique ever thrown at it. The light of the disk acts like fog, and the planet was a figure standing in that fog, invisible to the eye but perfectly detectable by its own chemistry. If astronomers can find planets in the worst viewing conditions nature has to offer, imagine what they can find in the best ones. The method opens a new lane in the search for exoplanets, complementing the transit method, which watches planets pass in front of their stars and dim them slightly, and the radial velocity method, which measures the gentle tug a planet exerts on its star. Every one of these techniques has blind spots, and together they have already revealed more than 5,000 confirmed planets beyond our solar system, a number that would have seemed like science fiction a generation ago. But the spectroscopic fingerprint method adds something genuinely new, the ability to find planets that are embedded in complex, dusty environments where other methods fail. It also points toward a deeper future, because the same technique that found Beta Pictoris d, reading the atmosphere of a hidden world, is the technique that will one day be used to search for signs of life on worlds like the famous K2-18b, where telescopes have already found tantalizing hints of molecules that, on Earth, are produced by living things. Webb has spent much of its time peering at such worlds, teasing out their chemistry and looking for the ingredients of biology, and the discovery of Beta Pictoris d proves that this approach is more powerful than anyone fully appreciated. It is capable not just of studying planets that are already known, but of discovering planets that have never been seen at all. The day is coming when a mission like the Nancy Grace Roman Space Telescope will sweep across the sky and find planets by the thousands. Some of them will be spotted in images, and some will be found exactly the way Beta Pictoris d was found, by listening to the light rather than looking at the picture. The same story is playing out in systems all across the Milky Way, and most of their planets are probably hidden from us right now, waiting for the right instrument and the right technique to reveal them. For the Beta Pictoris system itself, the future is just as rich, because the debris disk that hid the planet for so long is now a source of new questions, and the presence of the planet may explain some of the disk's strangest features. Astronomers had long puzzled over the disk's sharply defined inner edge, a boundary that seemed too clean to be natural, and over its warp, a bend in the disk that hinted at some unseen influence. The discovery of Beta Pictoris d offers a natural explanation. A massive planet on a wide orbit can sculpt the debris around it, shepherding dust and clearing gaps, stamping its gravitational signature on the material that surrounds it. The planet may even be the reason the inner edge of the disk looks the way it does, its gravity acting like a broom that sweeps the region clean. In fact, astronomers had already predicted that a planet like this one must exist to explain the disk's strange structure, and the discovery validates that prediction in the most satisfying way possible. The The system that taught astronomers how planetary systems form has now taught them a lesson about how planets hide and how to find them anyway. The team plans to keep analyzing their observations, refining their measurements of the planet's temperature, its atmospheric composition, and the details of its orbit, and each new pass through the data will sharpen the picture while follow-up observations with Webb add even more detail. There is every reason to think that Beta Pictoris dA has more secrets to give up, because every measurement of an exoplanet is an act of archaeology. We sift through light that left its surface ages ago, light that arrived at our telescopes carrying the whole history of its atmosphere inside it. The star itself, young and volatile, continues to evolve, and the planets around it continue to change, meaning that the system will remain a favorite target for astronomers for decades to come. It is a living classroom, where the story of our own solar system's adolescence is written in dust and gas and giant planets, and where every new observation adds another sentence to that story. Stepping back, the discovery is a perfect illustration of why the James Webb Space Telescope matters so much, because before Webb launched, astronomers could only dream of the kind of sensitivity the telescope has delivered as it stares deep into the infrared. Webb was designed to see the first galaxies, to study the atmospheres of distant worlds, and to look back in time nearly to the beginning of the universe, but its greatest gift may turn out to be the unexpected discoveries it makes along the way. The telescope has already found galaxies that appeared too early to exist, black holes that grew too fast, and chemistry around other stars that no one predicted. Now it has added a hidden planet to that list, a world that sat in plain view at the heart of one of the most studied systems in the sky. And the lesson is humbling. If a giant planet can hide from us for more than 40 years in a system we have photographed from every angle, how many other secrets are we walking past every night? How many worlds are hiding in plain sight right now, waiting for a telescope sharp enough and a technique clever enough to notice them? Part of the answer lies in the nature of scientific discovery itself, because astronomers do not simply point their instruments at the sky and collect what is there. They interpret what they see, and interpretation comes with blind spots. For decades, the standard way to find a planet was to see it, to catch its light directly, or to watch its shadow cross the face of its star. And the idea that a planet could be found by its chemistry alone, by the barcode of absorption lines in a spectrum, was known in theory but rarely applied to the search for new worlds. Beta Pictoris d changes that, and it does so at the perfect moment because the field of exoplanet science is exploding. Thousands of worlds are confirmed, and tens of thousands of candidates wait to be studied. And the greatest challenge is no longer finding planets, but understanding them. To understand a planet, you need its spectrum, and the discovery of Beta Pictoris d proves that the spectrum can sometimes be the very thing that reveals the planet in the first place. It folds the search for planets and the study of planets into a single act, an efficiency that will shape the next decade of astronomy. There is also a quieter lesson hidden inside this story, one about patience and preparation, because the team that found Beta Pictoris d was not using a new trick or a lucky shortcut. They were doing careful, methodical science, pointing a great telescope at a known system and reading the light that came back with meticulous attention. The discovery emerged not from brilliance alone, but from the patient accumulation of data, from the refusal to be fooled by a bright blob in an image, and from the willingness to trust a spectrum over a picture, and that discipline is the true engine of progress in astronomy. Webb is a marvel of engineering, a golden mirror the size of a tennis court unfolded in the cold darkness a million miles from Earth. But it is only as good as the people who use it and the questions they ask. The discovery of Beta Pictoris d was made possible by a telescope that can see farther than any before it, and by scientists who knew exactly what they were looking at when an unexpected pattern of light drifted into their field of view. Looking ahead, the discovery invites a simple and thrilling question. What else is hiding out there? The Milky Way is home to hundreds of billions of stars, and current evidence suggests that planets are the rule rather than the exception, meaning that most stars host at least one world. If a giant planet can hide inside a bright debris disk for decades, then the number of undiscovered worlds in our galaxy must be enormous. Some of them will be found by future surveys, some by Webb itself as it continues its mission, and some by telescopes that have not yet been built, while the technique proven at Beta Pictoris will be refined, applied to larger samples, and combined with other methods until the census of the galaxy's planets comes into focus. And somewhere in that census, almost certainly, there are worlds like our own, hiding in plain sight, waiting for a species that learned one star at a time how to see them. For now, the story belongs to Beta Pictoris d, a giant planet that spent its entire youth in the shadow of its own birthplace, masked by the debris of the same disk that made it. It is the third world discovered around a star that astronomers thought they knew completely, and its discovery is a monument to the idea that the universe is always richer than our current picture of it. 50 years ago, no one knew that planets existed beyond our solar system. 30 years ago, the first of them was found. 20 years ago, direct imaging of exoplanets was still a dream. Today, A hidden giant has been pulled from the fog by the power of its own chemistry, and tomorrow the same approach will be searching for other worlds, closer and more familiar, in the light of other suns. The James Webb Space Telescope finally revealed the planet hiding in plain sight, and in doing so, it showed us that plain sight is never quite as plain as it seems. The next world found this way could be closer than we think, and the discovery that finds it will owe a debt to a young star 63 light-years away, and to the astronomers who refused to accept that what they could see was all there was.